All right, the next strategy we're going to see for alpha alkylation is going to involve a slightly different pathway. We'll go over this mechanism carefully, but for right now, I wanted to show you the overall mechanism. And just like before, we're going to start out with some sort of alkyl halide or something with a good leaving group on it, like a tosylate. And after a handful of steps, what's going to happen is you're going to add a CH2 group, a carbon, and an OH. So really what you're going to be doing is you're going to be adding this entire group onto the position that used to be the halogen site, right? So it's a little bit interesting to think about this, right? If we think about this product, it's a carboxylic acid that we've created. The alpha position on the carboxylic acid is this carbon right here, which basically means that this R group is going to be the alpha alkylated site on the carboxylic acid. All right, so it's a bit different when we think about this, but let's take a look at the overall mechanism and figure out how we can make these alpha alkylated carboxylic acids directly from some sort of alkyl halide. All right, and here's the mechanism. The mechanism actually starts out with a different reagent, not our alkyl halide. What we're going to use is this di-ester reagent, where we've got ethyl esters off of each end. This is the classic one that's normally used. This reagent is called diethyl malonate. And if you remember, we went over diacids before, so if we swapped off each of these ethyl groups for a hydrogen, then it would just be malonic acid. That's why this is called diethyl malonate. And what we're going to do in the first step is we're going to treat this with a base. And just like with the Claisen condensation, we want to make sure that this base matches whatever our ester is, right? We don't want to do any transesterification. And the most acidic protons that we have are these ones in the middle. So we're going to go after these protons that are alpha to both carbonyls, and we're going to make an enolate. And now that we've got our enolate set up, what we can do is we can treat this with our alkyl halide. And just like we saw in the prior step, an enolate can do SN2 chemistry with an alkyl halide. So this is going to be SN2. However, we have to remember that this R group must be a methyl or a primary R group. Otherwise, we're not going to be able to do SN2 chemistry if it's hindered like a tertiary carbon. It needs to be relatively unhindered. All right, and so we'll be able to alkylate this central position and get this new halogen installed. Or sorry, new alkyl group installed. All right, now the next part is a little bit steppy, and it's a reaction we've seen before, so I'm just going to condense it down. But what we're going to do in the next step is treat it with dilute acid. And if you remember in our carboxylic acid derivative chapter, we said that esters can actually be hydrolyzed to carboxylic acids. So we're going to take both of these esters and we're going to convert them entirely to carboxylic acids. And if you want to practice that mechanism, you're more than welcome to. The first step is going to be protonation of this carbonyl. Then we'll have water attack in. Then we'll protonate this, kick it off. It's kind of a bit repetitive, so we're going to skip that for this video. All right, and what I want to do next is I want to show you a different way of drawing the same starting material. All right, so instead of drawing it the way I have shown above, I'm going to keep the right carboxylic acid as is. And I'm going to put the OH group for my carboxylic acid on the left-hand side kind of sticking up. So really these are the exact same compounds. We're just rotating this bond around a little bit. All right, now the interesting part. If we take these carboxylic acids and we apply heat to them, we can get a special reaction called the decarboxylation. And what's really happening here is we're getting an intramolecular H bond between that oxygen and hydrogen, right? And so what will occur is this will grab that hydrogen and form a new bond. At the same time, this will kick down, and then this will come over. Well, if that occurs, what happens is this entire group is essentially going to be lost, right? So when we think about this, we're going to end up with CO2 coming off as a leaving group. That's a gas, right? So we're just going to blow that off. It'll bubble out of solution. And then the remaining portion on the right-hand side is going to have a double bond here. We're going to have an OH here and here. However, when we really think about what we've created here, this is just an enol. And we know that enols will quickly tautomerize to their keto form, right? So that R group is going to stay put. We're going to end up with a double bond there and an alcohol over here. So we're just going from our enol to our carboxylic acid. And as you can see, we've got this alpha position on our carboxylic acid, and the R group, meaning that alkyl group, is now installed off of that. Like I said, this whole process is called a tautomerization. And a tautomerization, all that means is that it's a reaction where protons are moved around. So we're just interconverting these constitutional isomers by just moving protons around using solvent. In this case, it would be water. All right, so we're able to make this product pretty easily that way. All right, so let's see what we can do if we do this twice, which is kind of neat. This is called dye substitution. And with dye substitution, the unique thing with this is we're still going to start out with diethyl malonate. We're still going to treat it with a strong base like sodium ethoxide in our first step. That will rip off that middle alpha proton. And then we're going to treat this with some sort of alkyl halide. I'm just going to call this R, our red R. But then, after you do that, you're going to have this R group installed here, but you'll still have one alpha proton left over. So what you can do next is you can treat this again with another equivalent of sodium ethoxide, followed by a new alkyl halide. So really you're just repeating step one again with your second alpha proton. All right, so now by doing that, we can alkylate that center position twice. But after this point, we don't really have any more alpha protons to deprotonate because we've already used all of them, right? And then in our next step, what we're going to do is we're going to treat this with dilute acid and heat, right? And when we do this, first thing we're going to do is we're going to convert both of these esters to carboxylic acids, right? And then in our next step with this heat, what we're going to do is basically get rid of CO2 off of one of these sides. Doesn't really matter which one. I just like to pick the left-hand side one. And when we do this, we're going to be left with our carboxylic acid and our two R groups. One of them is red, one of them is blue, plus CO2 gas. So we're able to decarboxylate and get to this product where now we have two alkylations coming off of the alpha position of a carboxylic acid. So it's a kind of interesting process that way. All right, what we're going to do is we're going to stop there. And then when we come back, we're going to look at an alternate synthesis that's similar, but instead of making an alpha alkylated carboxylic acid, we're going to make an alpha alkylated ketone using a similar method.